evaluate the iterated integral. We're looking at the integral from 0 to 2 of the integral from 0 to y squared of x squared y dx dy. This is given as a type 1 integral, but I really don't usually talk about type 1 and type 2. There will be a time in a future chapter where we're going to see some of that, but not really right now. I just care that you can do the work. And our work is going to start by evaluating the innermost integral, which means integrating first with respect to x. And in fact, I'd like you to pause the video, work out the whole thing, and then come back when you're done. Hopefully when you integrated with respect to x, you ended up with the integral from 0 to 2 of 1/3 x cubed y. X is going to go from 0 to y squared, and we still will integrate with respect to y, so there's still a dy. Substituting y squared in place of x, we end up with the integral from 0 to 2 of 1/3 y to the 7th dy. Using the power rule yet again, we have 1/24 y to the 8th evaluated from 0 to 2 for a value of 32/3. Now let's take a moment to analyze the region D, and the region D is given by the limits of integration. We can see here that x would go from 0 to y squared, and that y would go from 0 to 2. I'm going to turn these limits into a graph in the xy plane. The curve y equals x squared, it looks like the square root function, doesn't it? And y goes from 0 to 2. That'll mean that x goes from 0 to 4, and now we have to decide, is this the one, is it going to be under the curve touching the x-axis or above the curve touching the y-axis? Well, x is going from 0 to y squared, so x starts at the y-axis and then goes to y squared. So we're looking at the region above the curve along the y-axis. Now we could, if we wanted to, reverse the order of integration, and in order to do so, what we would do is figure out limits on y, they would be variable limits, and then figure out limits on x, in either order. And in fact, let's go ahead and we can see that x is going to go from 0 to 4 for the region that we have now, thinking about the fact that x has to have constant limits if we're going to reverse the order. Y in this region is going to go from the curve to the horizontal line y equals 2, and the curve was given by y equals x, the curve was given by x equals y squared, which also means that this curve is y equals the square root of x, which is why it looks like the square root function, right? So y has a lower limit of the square root of x, an upper limit of 2, and looking at it this way, we can set up the integral using the reverse order. X goes from 0 to 4, y goes from the square root of x to 2. The integrand doesn't change, it's still x squared y, but we've now set it up so it doesn't go dx dy, but it goes dy dx. I encourage you to compute this integral just so you can verify that we get the same answer of 32/3. At this point, we did this reversing the order of integration just for kicks, really, just so you could see what the process is, but sometimes it's going to be necessary to do it, depending on what the integrand is. Yeah, that's pretty much it. It depends on the integrand. I'd also like to note that in this case, even though our integrand is x squared times y, we could split it as a function of x times a function of y. We cannot split this up into a product of two integrals because we have variable limits for the innermost integral.